Hello everyone. The learning objective for today is students will be able to describe the Earth's interior, its tectonic plates and their movements, and how mountains, volcanoes, and earthquakes are formed. Please open IS-3 Dynamic Earth Interactive on Nearpod. Thank you. IS-3 Earth's interior will be supplemented by the Dynamic Earth Interactive website. Our objective is students will be able to describe the Earth's interior, its tectonic plates and their movements, and how mountains, volcanoes, and earthquakes are formed. Our warm-up question is, what did you learn about the planet Earth in 7th or 8th grade? Provide at least one example. Click on the website Dynamic Earth Interactive with the link on the left. After completing the 4 lessons, take the test on the Test Skills page. Paste a screenshot of your score below. You need to earn a 70% or higher. On a Chromebook, the directions for how to screenshot are the Control button and Window Switcher button, and then go to the Nearpod screen. You may need to use the arrow or the crayon tool to click on the screen itself, and then to paste, push Control and V. Let's go through the entire website, and then at the end you will click on Test Skills. If you do not get a 70%, click on Test Skills again to try again. Introduction. The Earth. Think it's solid as a rock? Our planet might seem fixed and rigid, but a closer look reveals that it is constantly shifting under our feet. Delve into the Earth's interior, learn about its tectonic plates and their movements, and discover how mountains, volcanoes, and earthquakes are formed. Click on the red Start Your Exploration with Earth's Structure. Earth structure. What's inside the Earth? In the early part of the 20th century, geologists studied the vibrations, or seismic waves, generated by earthquakes to learn more about the structure of the Earth's interior. They discovered that it is made up of these distinct layers: the crust, the mantle, and the core. Take a few minutes to click on each one of these descriptions of the crust, mantle, inner core, and outer core. Read the description on the right, and also take a look on the top right. How much of the Earth's interior is the crust versus the mantle? When you're ready, click on Next Chapter, Plate Tectonics. Both of these are pictures of the Earth. Click on the one that looks more like the Earth today. That's right, it's the one on the right. Yes, the picture on the right shows the continents of the Earth as they appear today. The picture on the left shows the continents as they appeared long ago, approximately 250 million years ago. Click on the green, how do we know this? Plate tectonics. In the early 1900s, the German scientist Alfred Wegener noticed that the coastlines of Africa and South America looked like they might fit together. He also discovered evidence that the same plant and animal fossils were found along the coasts of these continents, although they were now separated by vast oceans. In addition, he noticed that geologic formations like mountain ranges on the two continents also matched up. In 1915, Wegener published his book, The Origin of Continents and Oceans, suggesting that the Earth's continents were once joined together in one large mass. He called the original landmass or supercontinent Pangaea, the Greek word for all the Earth. According to Wegener, over time, Pangaea split apart into different landmasses, or continents, drifted to their current locations on the globe. While other scientists of the time vehemently rejected Wegener's ideas, they became the basis for the development of the theory of plate tectonics. Continents on the move. 200 million years ago, Pangaea begins to break up and splits into two major landmasses. Laurasia in the north, made up of North America and Eurasia, and Gondwana in the south, made up of the other continents. 135 million years ago, Gondwana splinters further. The South America-Africa landmass separates from the Antarctica-Australia landmass. The Indian landmass breaks away from the Antarctica-Australia landmass. 65 million years ago, major rifting of Laurasia, with the North American landmass separating from Eurasia. South America and Madagascar separate from Africa. 50 to 40 million years ago, Greenland separates from North America. Australia separates from Antarctica and moves north. The Indian landmass collides with Asia. The modern plate tectonics theory, which has become widely accepted since the 1960s, states that the Earth's outer layer, or lithosphere, is broken into several large slabs called plates. These plates, which hold the continents and oceans, are slowly but constantly moving around the planet. The movement of the plates not only supports our understanding that continents are not fixed and move over time, but also explains how and why earthquakes, volcanoes, and other geologic events occur. Click on the red Continents over Time. See if you can trace how the Earth's continents have shifted over time. You will see a series of 5 images showing the positions of the Earth's continents during different geologic time periods. You will have 2 minutes to arrange them in the correct order. Drag each image onto the timeline, and when you are done, press the check button to see if you are right. Good work. Now see if you can answer the bonus question. Which of the images above represents the Earth as it might appear 250 million years from now? The answer is the second one. Pangea Ultima. That's right. Since the plates are constantly in motion, some scientists estimate that the continents will come together to form one large landmass again in the future. The image above is based on a map by Dr. C.R. Scotesi, showing what Pangea Ultima might look like. Move on to the next chapter, Plate Boundaries, to learn how plates interact. Plates and boundaries. The Earth's continents are constantly moving due to the motions of the tectonic plates. Closely examine the map below, which shows the 15 major tectonic plates. As you can see, some of the plates contain continents, while others are mostly under the ocean. The type of crust that underlies the continents is called a continental crust, while the type found under the oceans is called oceanic crust. Continental crust is thicker, about 20 to 40 miles or 35 to 70 kilometers thick, and usually older than oceanic crust, which is only 4 to 6 miles or 7 to 10 kilometers thick. All the plates have names, usually referring to land masses, oceans, or regions of the globe where they are located. Take a look at the map on the screen. You will be quizzed on this map in a challenge similar to the last slide. The border between two tectonic plates is called a boundary. All the tectonic plates are constantly moving, very slowly, around the planet, but in many different directions. Some are moving toward each other, some are moving apart, and some are sliding past each other. Because of these differences, tectonic plate boundaries are grouped into three main types. A convergent boundary occurs where two plates are pushing toward each other. Examples of convergent boundaries include the boundary between the Eurasian plate and the Indian plate at the Himalayas, the boundary between the Nazca plate and the South American plate along the west coast of South America. A divergent boundary marks two plates that are moving apart from each other. Examples of divergent boundaries include the boundary between the African plate and the Arabian plate in the Red Sea, the boundary between the Pacific and Antarctic plates, the Mid-Atlantic Ridge, made up of the boundary between the North American and Eurasian plates in the North Atlantic, crossing Iceland, and the South American and the African plates in the South Atlantic. A transform boundary occurs where two plates slide past each other. Examples of transform boundaries include the boundary between the Pacific plate and the Australian plate crossing New Zealand, the boundary between the Pacific plate and the North American plate in California. Use the map below to see where the three different types of plate boundaries are found throughout the world. First, find the key in the green box located at the bottom of the map. Then, select each boundary name in the key to see its location. Take a look at this map. You will also be quizzed on this map and the locations of different types of boundaries. Click on the Plates and Boundaries challenge. See how many of the tectonic plates and boundaries you can identify. This is a two-part challenge. First, you must correctly place the names of the major tectonic plates on the map. Then you must identify the type of boundary that is found at the borders between several of these plates. Click on How to Play. Drag each plate name to its correct location on the map. You will have one chance to get the right answer and 2 minutes to complete this part of the challenge. Click on Begin. An area on the map will flash and you must identify the type of boundary found at that location. You will have 1 minute to name all 6 boundaries and only one chance to get the answer right. Click on the question mark button for a hint. Click on Begin. Notice how the flashing boundary is white. This does not correspond to the white color shown in the map earlier. You need to recall what it was you learned. Again, if you don't remember, click on the question mark, and this will help you remember what the types of boundaries are. Once you are done with the challenge, click on the next chapter. Slip, slide, and collide. Red-hot lava and plumes of ash spew out of a volcano in the Philippines. An undersea earthquake in the Indian Ocean spawns a tsunami that crashes into Indonesia. The Himalayan mountains grow taller every year. Many of the most dramatic geological phenomena we experience on Earth, volcanic eruptions, earthquakes, tsunamis, and more, are caused by the slipping, sliding, and colliding of tectonic plates. As you might expect by now, most major geologic events occur at the boundaries between tectonic plates, where huge, massive pieces of the Earth's crust interact. Each kind of plate boundary is associated with particular events, so if you know about the movements taking place at a plate boundary, you can often predict what's likely to occur there: volcanoes, earthquakes, mountains, and trenches in the future. Click on See What Happens at Different Plate Boundaries. At convergent boundaries, tectonic plates collide with each other. The events that occur at these boundaries are linked to the types of plates, oceanic or continental, that are interacting. Subduction zones and volcanoes. At some convergent boundaries, an oceanic plate collides with a continental plate. Oceanic crust tends to be denser and thicker than continental crust, so the denser oceanic crust gets bent and pulled under, or subducted, beneath the lighter and thicker continental crust. This forms what is called a subduction zone. As the oceanic crust sinks, a deep oceanic trench, or valley, is formed at the edge of the continent. The crust continues to be forced deeper into the Earth, where high heat and pressure cause trapped water and other gases to be released from it. This, in turn, makes the base of the crust melt, forming magma. Select each label for additional information. Click on each one of these to see what these are. The magma formed at a subduction zone rises up toward the Earth's surface and builds up in magma chambers, where it feeds and creates volcanoes on the overriding plate. When this magma finds its way to the surface through a vent in the crust, the volcano erupts, expelling lava and ash. An example of this is the band of active volcanoes that encircle the Pacific Ocean, often referred to as the Ring of Fire. A subduction zone is also generated when two oceanic plates collide. The older plate is forced under the younger one, and it leads to the formation of chains of volcanic islands known as island arcs. Examples include the Mariana Islands in the western Pacific Ocean and the Aleutian Islands off the coast of Alaska. Since the collision and subduction of plates is not a smooth process, large, powerful earthquakes are another phenomenon that result from this type of interaction. Earthquakes generated in a huge subduction zone can also give rise to tsunamis. A tsunami is a huge ocean wave caused by sudden shift on the ocean floor, such as an undersea earthquake. If the wave reaches land, it can cause incredible destruction, like the Asian tsunami, which killed more than 200,000 people in 11 countries across the Indian Ocean region in December 2004. Collision zones and mountains. What happens when two continental plates collide? Because the rock making up continental plates is generally lighter and less dense than oceanic rock, it is too light to get pulled under the earth and turned into magma. Instead, a collision between two continental plates crunches and folds the rock at the boundary, lifting it up and leading to the formation of mountains and mountain ranges. Select each label for additional information. An example of this mountain building process is the Himalayan range in southern Asia. Containing the highest mountain peaks in the world and traversing the modern-day countries of India, Pakistan, China or Tibet, Bhutan, and Nepal. The Himalayas were formed by the collision of the Indian and Eurasian plates. This process began after the breakup of Pangaea, when India became an island continent and began traveling toward North Asia. The island of India slammed into Asia about 40 to 50 million years ago, near modern-day Tibet, crushing and folding the plates to form the Himalayan mountain range. Its best-known peaks, Mount Everest and K2, are among several that measure over 8,000 meters, or 26,000 feet, high at their summits. Since the Indian plate is continuing in its northward movement into Asia, the Himalayas continue to grow higher each year by small amounts, 5 to 20 millimeters, or 1 inch per year. Click on Next. Divergent boundaries, spreading plates. At divergent boundaries, tectonic plates are moving away from each other. But if these huge masses of crust are moving apart, what happens in the space left between them? Seafloor spreading. Divergent boundaries in the middle of the ocean contribute to seafloor spreading. As plates made of oceanic crust pull apart, a crack in the ocean floor appears. Magma then oozes up from the mantle to fill in the space between the plates, forming a raised ridge called a mid-ocean ridge. The magma also spreads outward, forming new ocean floor and new oceanic crust. Rifts. When two continental plates diverge, a valley-like rift develops. This rift is a dropped zone where the plates are pulling apart. As the crust widens and thins, valleys form in and around the area, as do volcanoes, which may become increasingly active. Early in the rift formation, streams and rivers flow into the low valleys, and long, narrow lakes can be created. Eventually, the widening crust along the boundary may become thin enough that a piece of the continent breaks off, forming a new tectonic plate. At this point, water from the ocean will rush in, forming a new sea or ocean basin in the rift zone. Transform boundaries, grinding plates. At transform boundaries, tectonic plates are not moving directly toward or directly away from each other. Instead, two tectonic plates grind past each other in a horizontal direction. This kind of boundary results in a fault, a crack, or fracture in the Earth's crust that is associated with this movement. Faults and earthquakes. Transform boundaries and the resulting faults produce many earthquakes because edges of tectonic plates are jagged rather than smooth. As the plates grind past each other, the jagged edges strike each other, catch, and stick, locking the plates in place for a time. Because the plates are locked together without moving, a lot of stress builds up at the fault line. This stress is released in quick bursts when the plates suddenly slip into new positions. The sudden movement is what we feel as the shaking and trembling of an earthquake. The motion of the plates at a transformed boundary has given this type of fault another name, a strike-slip fault. The best studied strike-slip fault is the San Andreas Fault in California. It is located at the boundary between the Pacific and the North American plates and runs roughly 800 miles or 1,300 kilometers through northern and southern California. As the two plates grind past each other, the Pacific plate moving northwest and the North American plate moving southeast, the motion produces numerous earthquakes along the fault. While many are small and cause only minor trembling, the San Andreas Fault has also been the site of major events. The 1857 Fort Tejon earthquake, the 1906 San Francisco earthquake and fire, and the 1989 Loma Prieta earthquake. Many scientists believe that the San Andreas Fault is due to unleash another large earthquake, a big one, in the coming decades. Click on Plate Interactions Challenge. See if you can figure out the plate movements and geologic events occurring at real-world locations. This is a two-part challenge. First, you must figure out what plate movements and geological events are occurring at 3 real-world locations. Then you will need to correctly identify 4 geologic terms. Click on How to Play. Examine these real-world cases of plate boundary interactions. Using your knowledge of plate tectonics, see if you can determine what's happening at each site. You will have 10 minutes to complete this part of the challenge. Click on Begin. Lightning round. Word jumble. You have to unscramble 4 geologic terms you've learned in this chapter. You will have 1 minute to unscramble each term. Click on Begin. When you are done with all of the pages, click on Test Skills. Answer questions related to dynamic earth. This is an assessment to see how much you've learned in this interactive. Answer the following questions, which will be scored and can be printed for review when you are done. If you can get at least a 70% or higher on this test, please screenshot your score and paste it into Nearpod. Thank you, everyone, and I will see you next time.